chemical quantities, and when we talk about quantities, we're going to be talking about amounts. So we have an actual amount or a number for specific substances. So in this topic, we go over chemical quantities related to chemical changes. When you have an initial substance and a chemical change happens, you're going to form new substances. So all of the amounts that are involved in a chemical change is what we're going to look at in this specific topic. So when we look at amounts for chemical changes, we're going to be looking at numbers with units. And depending on which number we have, we can have an amount given in a specific unit. The mole is the unit that we have for amount of substance. That's the unit that the International System of Units uses for amount of substance. But amount of substance can be given in grams, which is what we can actually measure in the lab, amount in grams, using a mass balance. So we have here Avogadro's number. Avogadro's number, 6.02 times 10 to the 23, tells us like how many particles or how many items you have in 1 mole. So the definition for 1 mole is that in 1 mole you're going to have 6.02 times 10 to the 23 particles. So the mole here, that equality, it's something similar to what we have in a day. In 1 day you have 24 hours. So in 1 mole you have 6.02 times 10 to the 23 particles. Any mole, 1 mole for any substance, it's always 6.02 times 10 to the 23. If we talk about 1 mole of paper, you're going to have 6.02 times 10 to the 23 sheets of paper. If we talk about a mole of pens, you're going to have 6.02 times 10 to the 23 pens in 1 mole of pens. So the word particle here, we're going to replace by different words depending on what we have. If we're talking about elements, when you have 1 mole of any element, what you have in 1 mole of an element is atoms of that element, because your elements are composed entirely of atoms. So this is my first one right here. If you have 1 mole of sodium, which is an element in the periodic table, element number 11, you're going to have, in every mole of sodium, you have 6.02 times 10 to the 23 atoms of sodium. If we're looking at molecules or covalent compounds, in a covalent compound, what you have, the simplest thing that you can use to describe that compound, it's a molecule of the compound. So looking at CO2, 2 nonmetals, that's a covalent compound. In every mole of CO2, what you have, it's 6.02 times 10 to the 23 molecules of CO2. And then the last example that I have here is when you have 1 mole of an ionic compound. In 1 mole of an ionic compound, what you have, it's formula units. So atoms, molecules, formula units refers to number of particles. It's how many particles we have in 1 mole. But that word particle is replaced by atom, molecule, or formula unit depending on what you have. If it's an element, instead of particles we say atoms. If it's a covalent or molecular compound, instead of particles we use the word molecules. And if what you have, it's an ionic compound, instead of the word particle, we're going to use formula units. So Avogadro's number, it's relating 2 different units for amount of substance. You have the unit, the mole, and you have number of particles. So this equality here, it's relating those two. In every mole, you have 6.02 times 10 to the 23 particles. Since you have an equality, you can represent that equality into two different conversion factors. Mole on top, number of particles on the bottom part, and the opposite here. Your number of particles on the top and the mole on the bottom part. So you can use your conversion factor to go from a number with units of moles to a number that is now giving you number of particles. Or if you're giving a number of particles, you can use these conversion factors here to go from your number of particles back to amount, but now with a unit of moles. So I have here 3 examples where we're going to use Avogadro's number as a conversion factor. So in the first one, you're given number of moles of carbon and you're trying to find out the number of atoms that you have. Avogadro's number is telling you that in every mole of carbon, you have 6.02 times 10 to the 23 atoms of carbon. So in this case, the problem is asking you, okay, if instead of having 1 mole of carbon, you have 2 moles of carbon, how many atoms of carbon are you going to have? So we solve these problems in the same way that we solve any problem where we're trying to convert one unit to another one. So the conversion factor between moles and number of particles is your Avogadro's number. The given quantity has units of moles, and you're trying to get number of atoms, which is the number of particles. So this is what you're trying to calculate, number of particles. So you need your conversion factor with number of particles in the top part, because that's what you're trying to calculate, and unit of mole in the bottom part of your conversion factor, because that's the given one and you want to cancel that one. So you're going to start your problem with the given. That's the given times your conversion factor, which is Avogadro's number, because you're trying to go from a number with units of moles to a number in units of atoms or number of particles. So out of my 2 possible conversion factors, the one that I have to use is this one. If you use this one here, you have more on the top part of your conversion factor, and you cannot cancel out this unit with that conversion factor. So we need this one. So you're trying to calculate atoms, so the number of particles is your number of atoms. So this will be 2 times your Avogadro's number divided by 1. Units, mole is canceling out, and you're going to get a number in units of atoms, which is your amount of atoms of carbon that you have if instead of 1 mole of carbon you have 2 moles of carbon. In 1 mole you have that amount. In 2 moles of carbon now you have this amount here. Second example, it's the same calculation. You're given number of moles and you're trying to get number of particles. So from moles to molecules, which is your number of particles, you have to use exactly the same conversion factor. In the third one, you're given moles of sodium chloride, and you're trying to find out the number of particles, formula units, which is exactly the same thing that you're doing in these other two problems here. You're given moles and you're trying to find number of particles, and I have my different words because carbon is an element, so that's atoms. Water, it's a covalent compound, that's molecules. And sodium chloride, it's an ionic compound, so that's a number of formula units. So I'm not doing the calculation, I'm giving you the answer. The calculation is exactly the same one that I already did, but you should do the calculation and you should check the number. Now, I'm not doing the calculation because you should try to do it on your own, and also because by definition 1 mole of any substance contains 6.02 times 10 to the 23 particles. So the amounts that you have for all three different substances here, it's 2 moles. So 2 moles, 2 moles, and 2 moles. If 1 mole contains the same number of particles for any substance, when you have 2 moles, you're going to have exactly the same number of particles for all three substances that I'm listing here. So whenever you get a chance, do your calculation and check that you're getting exactly the same number. The definition of 1 mole is 6.02 times 10 to the 23 particles. So if you have 2 moles of any substance, you're going to have twice as many particles because you have twice as many moles. Now this problem here, we're still using Avogadro's number because we have units of atoms and moles. So what relates moles and number of atoms, which is a number of particles, it's Avogadro's number. It's a similar type of calculation, but we're going from atoms to moles instead of from moles to number of particles. So the given now is the number of particles, and we're trying to get number of moles. So I have my 2 conversion factors here, my 2 possible conversion factors. And if the given number has here number of particles and you're trying to get moles, the one that you're trying to find out needs to be on the top part of your conversion factor, which means that now we need to use Avogadro's number in this configuration here, 1 mole over your number of particles. Units that are canceling out, this is 2.33 times 10 to the 24 atoms of iron times 1 mole. All of that divided by 6.02 times 10 to the 23 atoms of iron. So your atoms are canceling out the unit, and you're getting now a number that has units of moles. Now, when you're doing a calculation where you have to divide by Avogadro's number, I recommend that you put your numbers in parentheses. Whenever you're plugging your numbers in your calculator, you should put them in parentheses. Depending on the type of calculator that you're using, you might get a number that is 10 to the 40 something. So if you're getting an exponent that is 40 something, your calculator is doing 2.33 times 10 to the 24 divided by 6.02, and whatever number you're getting from that division, it's multiplied by 10 to the 23. So you have to make sure that you put your numbers in parentheses. So I'm getting something close to 4 moles of iron. If you have 1 mole of iron, you have 6.02 times 10 to the 23 atoms of iron, right? So this number here, it's a number that it's bigger than your Avogadro's number. You have 10 to the 24. So this number is bigger. If you have more atoms, you're going to have a number for moles that is going to be higher than 1. If this is what you have in 1 mole, if you have atoms here 10 to the 24, your number of moles should be higher than 1, which is what you're getting, something higher than 1. So for the next two here, you're doing exactly the same calculation. You're going from a number of molecules to number of moles, and molecules is your number of particles, and you're going again from the number of formula units, which is your number of particles, to number of moles. So you're using the same conversion factor, 1 mole over Avogadro's number for all of them, because that's what you're trying to get, moles. So I have here my diagram that I use for conversion between 2 different units. If I have a conversion factor that relates 2 different units, any conversion factor that you have like that, you can do this diagram here. So for these examples here, for the 3 of them, you're given number of particles and you're going to number of moles. Okay? What you have, what you want, what you have, what you want, what you have, what you want. Okay? So for all of them, you have number of particles and you're trying to get the number of moles. So what you have here is your number of particles divided by Avogadro's number. So whenever you're given number of particles and you want to get number of moles, you have to divide your number of particles by Avogadro's number, and that will give you the number of moles. The other way around, if you're given number of moles and you're trying to find out number of particles, which means that you're trying to calculate number of atoms, number of molecules, or number of formula units, what you're doing is what we did in this problem here. You have number of moles and you're trying to get number of particles, which in this example is the number of atoms. So you're multiplying your moles times your Avogadro's number. So whenever you have number of moles and you need to find out number of particles, this is what you have to do. You need to multiply by Avogadro's number. So this is our first conversion factor out of 2 that we're going to be using in chemical quantities. Avogadro's number that relates